Okay, so I can start. So I'm Vasilis Karakasis, working for CSCS, and I'm going to present our early experiences on porting a neuroscience code called NestMC. I'm going to talk about this a bit later. To KNL using Intrinsics. It's a work in progress, so I'm going to present mostly. I'm not going to focus so much on optimization stuff. I think already the previous talks were quite into that, and we just have a baseline that we can start working further from that point. So I'm going to talk mostly about cool things when working with Intrinsics and also some turndowns. Okay, I'm going to use this. So I'm going to talk a bit about what is NestMC, a bit of its design and architecture. I'm going to show which are the critical steps for, in terms of time for this simulation. And then I'm going through the backend that we use to translate a domain-specific language to actual C++ code that basically does the HPC part, the part that is the most computational intensive. And then I'm going to talk a bit about our experiences with using Intrinsics for KNL. So, well, NestMC is a project that wants to develop a new neuron simulator, multi-compartment, which basically multi-compartment simulators are simulators that the connections between the neurons and the cells are divided into compartments, and then there is done a simulation in each compartment, like a finite volume or finite differences, and this provides more accurate results, but it's quite computationally demanding. The second target is that we want to be optimized for HPC systems from the ground up, from the very beginning of the development process. And another goal is to be easy to integrate with other tools. This is basically a collaboration between different HPC centers, our center, ULIH, and BSC. And it's also part of the Human Brain Project at the NEST initiative. NEST is, again, a neurosimulation code that is mostly focuses on large simulations and not just inside what's going in each neuron in its cell. It simulates basically the communication, and it's quite for large networks. So the multi-compartment version, which is called NestMC, that we developed, is like a side product of the Nest, because it focuses on each neuron and how the cell is simulated. Well, I'm not a neuroscientist, so I might be saying I'm mostly a computer scientist, so this is my feeling of the whole field. So there's why we took the decision to develop a new multi-compartment neuron simulator is because the current solutions have several limitations. One is that the solutions for multi-compartment cell simulations, they don't treat very well large networks, and the problem is the real-time or near real-time simulations. And from the computer science perspective are the new HPC architectures. Most of these simulators that they exist, they were developed years before, and they now have a large, huge code base, and their porting to new architecture is not quite easy. So all you know, in this session, we have very highly parallel architectures that, like KNL. We have also GPUs. So we need to write a code to adapt and to engineer the code right from the beginning to be able to address those architectures. So that was the key motivation. As I said before, the goals is, first of all, we want at the user API level, we want the code to act as a library and provide an interface so that it can be easily integrated as part of a larger series of tools. But also internally, it's designed in a layered fashion. So there are several internal APIs so that you can plug in different modules, even for cell simulation or for SPI communication and a different integration scheme. So even internally, it's layered. So I'm going to show in one of the next slides how this looks like conceptually. And of course, the third goal is performance. It's designed from the beginning, having in the back of our minds to run on new highly parallel architectures. So, as you can see, this is the different layers of the design. So, and each layer is separated from the other one with interfaces. So here is how a model is executed, and then you have specific modules for example, the cell simulation and how you exchange the spikes. This can be, for example, implemented in different ways. For example, the spike exchange, you have MPI implementation or TBB implementation or both. And similarly, for the cell simulation, you have you describe basically your model. There is an interface in C++ internal inside the code, and then you have different backends for CUDA, for CPU, for KNL. You can create different backups. And also another important thing is that you can have the description of the model in standard DSL language. I'm going to talk about this a bit later. And also in the future, we plan also to have different interfaces for specifying the model for the simulation, like a Python interface or these kind of things, like higher level languages that they will be interpreted in actual library calls to our framework, which will then translate to highly optimized code. Currently, we have implemented a finite volume solver for the cell simulation, and this basically generates their backends for generating CPQ kernels or vectorized kernel that I'm talking about in this presentation, GPQ kernels. And all these take their specification for a domain-specific language, which is specific for neuroscience. So there, for example, a single statement might translate in a tight loop. Here is the basic time loop of the algorithm. First, we set up the spike buffers. This is basically a scheme for double buffering for the communication, so as to be able to overlap communication and computation. And then we start a parallel, basically, section. We first exchange the spikes. This is basically an all-to-all communication step that happens also inside the node, but also at center. At certain intervals, we have also communication between the nodes. And then it's the main computational loop, where there are basically 3 steps. First, we update the currents from the different ion channels. And from the computational point of view, this has some indirect memory references, because you have the compartment indices, and then basically the array where the vectors or the voltages are stored are indexed on this compartment based on this compartment index. So the references are not sequential necessarily. Next is a linear system solution, and then we integrate the state of the gating variables. This is also a bit computationally intensive, because there's lots of exponentials and transcendental functions. So as I said, for the CPUs, those 2 are the most time-consuming parts. On the GPUs, on the other hand, the linear solution of linear system was a bit higher, and now it's a different issue. So the key thing now is that basically the code that is associated with with these steps is generated by, or can be generated from, can be specified from this domain-specific language. And so the user can write in this language, and this is translated to the most time-consuming part of the kernel. So it is crucial to implement this efficiently. For that reason, we have built a source-to-source compiler that reads this language and then produces C++ code that integrates with the rest of the framework. And as I said, we have different backends. So the architecture of this compiler is, well, it's like of a typical simplified compiler. We get the N model source, we do an analysis, and then we have the AST of this language, and we go through it, and then we emit C++ code. For example, as I said, there might be statements that maybe generate a whole bunch of loops, and that's the purpose of domain-specific languages. So I'm going to talk, as I said, about the KNL part of this. So first of all, we started with the CPU code, and basically we used, so the modcc compiler generated standard CPU code, and we used then the ICC compiler to compile it without any pragmas at all, just whatever it can figure out from auto-vectorization. And so this is our baseline benchmark performance was about 50 seconds. And this is a simulation of, it's a parallel simulation on a single node. So we're using the whole single node. I think it's 2,000 cells and with 2,000 synapses per cell. And for the record, I think GCC was twice as much the performance. So Intel compiler was able to vectorize some loops, but we could still do better. So the next step was to do the guided compiler optimization. That was our first attempt. And we were managed to get twice as much the performance. But the problem here is that well, of course, we have to force the compiler to do the vectorization with IVDEP pragma. And for some mechanisms, there is a tricky part, though. Because, as I said, when you're updating the currents, then the accesses are indirect. And that wouldn't be a problem if the indices weren't aliased with each other. So you could just do a gather, and then do your computations, and then do a scatter, and you would be fine. But the problem is that if you have, for example, two indices point to the same location in the target current or voltage array, then if you just say IVDEP, then it won't work, because there is a dependency, and basically you say the compiling glory that just go and do aggressive vectorization. So in order to be able to guide the compiler, we had basically to change the loop. So we kind of did a blocking, so we're moving by SIMD vector length, and then we're doing a manual step of updating the individual vector elements. So next step was we write the kernel with Intrinsics. I'm going to reason about why we moved to Intrinsics, although we see a very slight performance degradation, like 2.6% from the optimized guided compilation. But this is just the first attempt. So we haven't dived yet into the code. For example, we're using analyzed memory accesses just to be safe. So it's the first attempt. And so the apparent question is, why do you use Intrinsics? So first of all, we want to support other compilers like GCC, which are not so adept in vectorizing or auto-vectorizing, or Clang compiler. And in any case, it's not that we have every time for each mechanism to implement it again in Intrinsics. We're writing a compiler backend, then we undertake this overhead only once, and then we can adapt just this step, and then whenever somebody writes a mechanism, then it will be vectorized. And another thing is that we want at some point to dive deeper. This is our next step, deeper in actual optimizations. So Intrinsics helps us to do that. And well, at this point, we didn't want to just add another dependency to another high-level C++ library that does the fancy stuff of overloading of defining vector types, overloading the operators, and doing everything for you. So we wanted, since, as I said, we're writing like a compiler backend, we want to have more control. So some things that I found helpful during this process is, first of all, a nice thing about Intrinsics. I saw some examples where Intrinsics coding was like assembly, basically. You load the other variable and so on, then you add two register variables. But actually, I found very useful that you can change, because you can change the Intrinsics. So basically, it's like a prefix notation. So this statement could be also written like that. And that's because you have the C++ interface of the Intrinsics. It's close to the assembly, but also gives you the programming ability and all the facilities. And this, from the compiler point of view, was also useful, because you went through the expressions and we're just emitting a prefix notation. And it didn't hurt the performance, because after all, it's the compiler that will get the Intrinsics code and do its steps of optimizations. Well, indirect accesses is, well, at least for the KNL, is now easy to implement because you have the scatter and gather. So usually it's an instruction that you get the indices. Here are integers. So you let them to a register, and then you use that register and do a gather. And then you work on that, do whatever you like, and then you do a scatter. This pattern repeats itself a lot. So there's places that usually we have a single gather, and then you may have multiple scatters. But as I said, this is not always the case, because it can only work if you know that. For example, here we wanted to accumulate some values on the V, but if your index is alias, then you have problem. You can't just do a scatter, do a reduction operation and do a scatter. Then you have then to go through the vector elements and accumulate manually. Another useful trick is. Basically, you can treat a vector type, and we can do this a fancy cast, and then you can work on it like normal dubs or floats. So if at some point you're going to go through each vector element individually, this would work. So basically, suppose that the compiler will, either dump it to memory and then go through it, dump this variable to memory and then go through it through this tight loop, or if it's clever enough, if he could just split it in different registers. At this point, we use this construct, but we have not yet, as I said, dived into the details. Probably we can change it, but it's quite useful as a workaround. So, as I said, we had several exponentials, logarithmics, and some power expressions. I first tried the ER instructions, but my unit tests were comparing the standard library versus the hardware instruction. And then I don't know if I have done something wrong, but they were accumulating error very quickly. So then I found the SVML. I'll talk a bit about this later. Another thing about the ER instruction is that they are all base 2. So you have to. Usually you have base 10 algorithms or logarithms or exponentials, so you have to convert. So you have to do twice the exponential one to complete to have the base, and then use the instruction. So I ended up using the sort vector math library, which is quite useful because, as we've seen in previous presentations, you have all the standard library transcendentals, and they have the look and feel of normal intrinsics. So you can just use them. You can even chain them with other intrinsics, so you can end up easily with a good code. The other thing is that they provide you with several common vector operations. For example, when I was trying, okay, how do I want a value? I want to broadcast it to all the elements. And there's no such instruction. So basically, they do it there. Set it there, you have a value. I want to broadcast to all the places of a vector, which is quite common. For example, is to zero out of, or not to zero out of vector, to set like 1 to the whole vector and like constants. This is very useful. And other such small vectors. So some turndowns. Of course, I mean, since you're going low level, subtle bugs might creep in. So then you can add it with segmentation faults, and then you're looking, okay, I think I'm doing fine. What's the problem? And then you might see that in a gather operation, you have not used the correct stride because you misinterpreted a bit the intrinsics guide. So you should be prepared to get into such things. Another, as I showed, as a first implementation, you might not do better than the Intel compiler. But at the end, I mean, if you dive into, I think that you can beat it. That's the purpose of it. But still, at least at our version, we are at the same level. That was our first goal, to have a first implementation with intrinsics to be at the same level with the compiler, and then so they can move on. What I found a turndown, I talked also with the guys here, is that SVML is practically unusable outside the Intel compiler, at least from what I have investigated until now. There is a workaround with GCC that I can show you in the next slide, but this is a real problem because our common function, you will always go through them, like all the transcendentals. And then there are some libraries that they don't have, for example, AVX 512 support. But you have SVML, and why not being completely public and go out there and be able to use it? So I'm going to show you, just for reference, the equivalent, how you would achieve the MM512 XPD. So basically, the only way to get, or to hint the GCC compiler to get a vectorized call, you have to do this. There is no such thing as an intrinsics function or a directly visible transcendental vectorized operation. So you have to go, for example, this is the interface of the SVML intrinsic. So basically, you have to go through the vector and just call stdx, and then retranslate these individual doubles and return a large vector double. But that's not enough. That's really not enough. You have to specify, well, look, GCC, I want to use the special vector library ABI to be SVML. There are also some other kinds from AMD. As Hans told in his previous presentation, you have to pass, also when you do just intrinsics with GCC, you have to pass the flag for the instruction set you're targeting. But still not enough. You have to use the OFAST, which is basically minus fast math, plus the tree loop vectorized. Everything is summarized in OFAST. So basically, you need F3 loop vectorized, which is enabled with O3, plus FFast math, which is equivalent to OFAST, which is not basic. Usually, you can do this in parts of the code with pragmas, but it's not necessarily. Not all people want to do OFAST to get this exponential vectorized. So all these things, and then you don't get AVX 512 call. You get two AVX2 calls. So still. well, programming with Intrinsics is not as scary or as difficult as it seems. Well, probably I'm saying that because I have a computer science background, but it's not that bad. And one thing is that the extra effort I believe can really pay off with especially non-Intel compilers. And you have finer control over generated code, and then for me, the shortcomings, or basically the showstopper at this moment, is the SVML and transcendentals. So my advice generally for Intrinsic is do it with care and whenever it's useful, and you think it is needed, and it can pay off for what you're doing. And finally, these are a bit more information. We have a prototype already publicly available. We basically actively developing on GitHub. So you can see the issues, you can see everything there. It's under BSD license. We regularly try with all these compilers, GCC like Intel, so the code compiles with all of this. However, the KNL backend is only guaranteed to compile with Intel compiler, unfortunately right now. We have CPU, GPU, that is CUDA backends, and MPI versions, and also you can use different on-node parallelism. Currently, we are supporting Intel TBB or simply pthreads. So that's it.
Any questions?
Maybe a non-recorded comment. We would love to have it. So it was a major step for us to convince the GCC community to allow SVML as a backend for their vector API.
Mm-hmm.
But it's hard for us to convince them to take the patches to actually enable the intrinsics. So there are SVML intrinsics in our header files supported by Intel. It's just that GCC doesn't support them. And we can give them a patch, but it doesn't necessarily mean that they're going to like the patch.
Yes, when I was trying to see, before finding this weird way, I tried to do some tricks, like picking the headers from Intel or writing my prototypes so as to cheat the compiler, but still it's not that easy because the type representations are, you can pass the compilation and linking phases, but then not the linking phase, the compilation, and then you were stuck in linking because the vector types used internally for GCC are different from Intel compiler. So basically, although both types are called like MM512, the internal representation is different. So yeah, it's a bit tricky. But do you plan like making available the library as a separate package so that somebody gets it, compiles it, and
well, the problem is, as far as I know, SVML doesn't use standard linkage.
Yes, I noticed that.
Something weird.
Yeah, I noticed that. You couldn't find any symbol, basically. It ended up with a VML whatever thing, X whatever, and no idea about the types.
Right, so one thing that you could do, though, is, I know it's not, the workaround is not going to be as beautiful as the one that you've been showing on the slides. But basically what you can do is, if you write inline assembly, you can call SVML directly. Right?
Mm-hmm.
You just need to pass the right thing in the right registers, and then you can call it, and then you would still need a small wrapper function around it that basically provides you with standard C linkage and standard C API. But that's also not very useful.
Yeah.
But you could also compile SVML into a different library that you just link with.
But yeah, where do I have the source for SVML to compile?
You just build that library with the compiler, and then you will make it part of the package.
Okay. Yeah, we can take it offline. Yeah.
All right, let's take the speaker and
Here.